Is this okay? Okay. So just a couple of quick public service announcements here. So it looks like it's pretty nice outside, but someone's left an umbrella up here. It was actually here last week, so it's probably not any of you, but just remember this, like if it's raining sometime when you leave, there's an umbrella up here. There's all sorts of weird stuff that gets left up here. Once I gave a class where someone had left like a gig bag for guitars, and it was like right up like by the podium for like 2 weeks before someone collected it. It didn't fit my guitar, so that's why. There's also, if anyone's hungry, there's a banana, right on the podium there. Just come on up. It's a little bit like browner than I like them, but some people like them like that. So they're very healthy. Okay. So I don't have any real announcements today. Are there real questions? Process questions or something? I kind of sometimes don't like Piazza because it's like I never talk to people face to face. It's just get these Piazza questions. So let me just do a quick recap of last week, if you guys remember. So last week we kind of we spent a bunch of time doing some math, pretty simple math, but it was math. So we were talking about this very simple algorithm called the perceptron algorithm, this is possibly the simplest learning algorithm you can imagine. You have a weight vector, which is vk. So k is the kth weight vector you kind of explore in your online learning process. When you get an example, the ith example, you just do a dot product and you take the sign. So you'll predict either +1 or -1 as whether it's a positive or negative example. And then if you're wrong, you do this update, right? So if the example was negative and you said it was positive, you subtract it from your weight vector. And conversely, if you made the other kind of mistake, then you add it. And interestingly, I proved that you could actually make a strong statement about how well this converge in a really weird kind of adversarial situation. There's no distribution these examples are drawn from. Instead, the adversary is going to give examples to the learner, and we're going to charge the learner with the number of mistakes they make. And the constraints on the adversary are two. Basically, you should give relatively clean, noise-free examples. So basically, there has to be some real weight vector that would separate the positive and negative examples. And we can say they're separable by basically saying that the label I give times the actual dot product is positive. All right, and furthermore, they have to be at least a little bit positive. So gamma is more than 0, so you have to be positive over some threshold, not really close to 0. This has a 2 norm of 1, okay, so its Euclidean length is 1. And the examples are all have 2 norms of R, okay? So they're not that large, all right? So if you want to look at that in pictures, here's a picture in 2 dimensions. So there's a true plane that separates the data, okay, which is this line, all right? So to figure out whether something's positive or negative, we look at its dot product with the thing that's perpendicular to that decision boundary. So if it's positive, then we'll give it a positive score, and if it's negative, we'll give it a negative score. And they have to be close to the origin, so they're in some distance from the origin. Okay, so they have to be in this circle, and this part of the circle with the red is the negative examples. This part with the green is the positive examples, and they're not allowed to be too close to this decision boundary. All right, so they have to be at least distance gamma away from the decision boundary, which basically means not in this little yellow stripe. Okay, so this is the constraints on the example and what the examples can look like. And if those constraints hold, then you get this kind of surprising result, which is the number of mistakes you make is bounded by r over gamma, okay, squared. So that was the first algorithm. And then toward the end of the lecture, I said, well, we're actually going to ramp this up and use a slightly different algorithm. And I talked about two variations, right? One algorithm is, so the essential problem is we have an online process, and at the end of the day, I just want to have one classifier that I can use on test examples coming in. So the online process is really sort of a proxy for what I'm really interested in, was getting a single classifier at the end of the day. And in the online process, we explore many different classifiers. So in these 10 examples, you explored, I guess, 4, right, counting the 0 vector that you start with. So which of these do you pick? So there was a probabilistic strategy which basically said you pick your example basically uniformly at random from this space, right? So we look at all the trials. I've had m trials. Here m is 10, right? And I just pick one of those at random. Or if you like, I'm picking something weighted according to how many examples it was used for, how long it persisted before it got changed. And then we predict using that example. So that gives us a vote, essentially. It gives us a, yeah, question?
Does the order matter in this online learning process?
I'm sorry?
Does the order matter in this?
Does the order matter? It doesn't. So the order matters in the sense that with a different ordering of examples, you'll get a different order of hypotheses. In fact, you'll get a different set of hypotheses, right? In this, turning this sequence of hypotheses into a voting algorithm, the order doesn't really matter, just basically how long they persist. And there's actually a deterministic approximation of this, so it's a little bit inconvenient. Let's say you've been training something for 100,000 examples, so maybe you've got 10,000 different perceptron hypotheses you've seen over time. So now you've got to basically do some sort of probabilistic or maybe a voting scheme over those 10,000 examples. That's kind of awkward, or there's 10,000 weight vectors. So what you can do instead is you can basically average them out. So averaging them out is a hack, but it seems to work pretty well. So what you basically do is you take each vector, you weight it by how long it persisted. So this is, MK is the number of examples that it was used for. So that's the number of things it got right plus 1 where it changed, okay? Divided by the total number of examples. So you weight them according to how long they persisted, and then you just average them all up. What we saw is that, this voted perceptron is one of these two lines, and the average perceptron is the other one of these two lines. And they're very, very close. They both do much better than, say, just picking the last one or taking a random one, a single random one non-deterministically. We haven't quite closed the loop because we don't have a full analysis of why this works, but it seems to work pretty well. We know why it converges and makes a small number of mistakes. And that's sort of a relatively easy analysis we can sort of put in our heads. So just to drill this down a little bit more, this is kind of what I was getting to at the very end of the lecture on last Thursday. What does this algorithm look like? It basically looks like this. We're going to start out, our initial hypothesis is just an all zeros vector, okay? So, we might just omit a hash table for that. And then for every example, we've got an x, which is a vector, and y, which is plus 1 or minus 1. If we get the right answer, we do nothing. Otherwise, we'll basically just add to our current hypothesis v, all right? So notice this is a sparse update, right? I'm just adding x. So the only attribute, if the vi is the ith feature, okay, then the only ones we're changing are the ones that are non-zero in the example. So this is a sparse update. Unfortunately, this doesn't work that well. This is, if I'm basically just taking the last hypothesis, then I get this very jumpy line right here, okay? So what works better is to take the average. So here's code for doing the average. So I've got two hypotheses. VK is the current hypothesis, and VA is the average. I'm going to just sort of maintain a running average. So I have to keep track of how long it's been that an example has been active. You start off, whenever you construct a new VK, you set this count MK to be 1, right? And whenever it makes no mistake, right, whenever it gets the right answer, you increment it, right? Otherwise, we're basically going to change VK, so we're going to give you a new VK. We're going to set MK to be 1. And for all these things, actually, this is the wrong place. This should actually be under the for each example, because this is basically counting the total number of examples you've seen, right? So this should actually be moved. Let me just move this up if I can. This should actually be up here, right? Because this is kept, no, wait, not that one. I'll get it right. This one. This is just basically counting every example we've seen. All right. Okay. Whenever I construct a new thing, I'm going to add it into the average. I don't know what the denominator is yet, right? I want to weight it by MK over M. I don't know what M is yet. So I'll just weight it by the number of times it's persisted and keep track of M, and then at the end of the day, I'll just divide the total average by M, okay? So that's the average perceptron, okay? So if you implement this, you'll see that you're spending almost all your time in this one step right here. This doesn't happen very often. It will give you much better performance, but whenever this happens, you're doing an update. You're taking an average perceptron and you're adding another VK. This thing is no longer sparse, right? This could have be the result of many, many different updates, so it could have lots and lots of features that are non-zero. So this update right here is about the size of the vocabulary. It's ordered the size of the vocabulary, all right? So before I had something which was basically linear in the number of non-zero features in the data set, all right? So that's fast, okay? And now I've gone to something which is order, maybe not n, the number of mistakes, but maybe it's like some fraction of n. You know, maybe it's like 1% of n or 10% of n, depending on what the data looks like. But some large fraction of n, there'll be one of these updates where you're updating the average, and that'll be really expensive. All right? So this is just like the case when you go from logistic regression to logistic regression with L2 regularization. You take this huge hit in efficiency on large data sets. When you make what seems like a pretty small change to the algorithm. So mathematically, it's not too much more complex, but it's much more computationally complex. All right? But just like there was for logistic regression, there's a trick we can do. So this is not a recap. I didn't get to this on Thursday. All right? We can take this algorithm for the average perceptron and fiddle around with it so everything gets sparse, okay? So here's an alternative version of the algorithm. So in the first version of the algorithm, I basically described it just exactly the way it is in the spec, right? The average is going to be a weighted sum of all the VKs. As soon as you have a VK, you update that average, okay? So as soon as you get a new perceptron hypothesis, you update the average. If you kind of think about it, another possibility, and this seems like it's taking a step in the wrong direction in terms of efficiency, but another possibility would be to basically just update the average perceptron with the current perceptron for every example. Then the total number of times that VA will be incremented by VK, right, will be exactly the number of times that VK is active, okay? So that's all right. All right, and at the end of the day, I just basically do the same thing. Of course, now I'm doing more of these updates, okay? But we're going to be tricky and we're going to reduce these updates. This is really here so we can understand what's going on a little bit more easily. All right. So here we're adding VK. So let's ask what VK is. All right. So VK is basically the sum of all the examples that we've made mistakes on, you know, with a +1 or -1. Okay. So so VK is basically the sum over all the indices where we've actually made a mistake in the past of yj times xj, right? So that's what VK is. It gets incremented that way, right? So whenever I see VK, I could think about just replacing it with that sum, all right? So what would happen if I replaced it with this sum? Then we can sort of see what's going on here, right? So basically, whenever I do this update, which I'm doing basically for every example, all right, I'm adding into VA, the average, all of the past cases where, the examples where I've made a mistake. All right, so that's what VA is, okay? As soon as I make a mistake on an example, then essentially every example after that, I'm going to be adding YI or YJ to the average, all right? So as soon as I make this mistake, this example X here gets added to my set of cases where I made a mistake, and then every iteration over that, I'm going to be adding it to VA, okay? All right, so now we can see why we can actually make this faster, right? What we could do instead of adding this thing many, many times is we can just add it in here once, okay? Right, it's going to get added every iteration after that, okay? Let's add one more piece of information, the total number of examples I'm going to go over. Let's say I'm going to do it over, you know, iterate over the data set 10 times, all right? So we know how many, and we know how big the stream is, so we know exactly how many examples we're going to see. So I can tell you how many times we're going to add it, right? It's basically the total number of times, discarding the m that we've seen so far, right? Then we're going to add this example times y to the average, okay? So that's a big change, okay? Because we're going through here, in the worst case, this happens for every example, right? But what we're adding here is we're adding x times y to vk, my current hypothesis, and that is just, you know, linear in the number of non-zero features of x. That's a sparse update, okay? And this one is also a sparse update, okay? Well, it's kind of like many, many sparse updates, but it's basically a sparse update, right? So that's the basic idea, and then at the end of the day, I just average it out by dividing by t, okay? So this is, again, basically a way to remind you that when you start doing these dense updates, the first thing you should do is kind of sit down and think about what's really going on and think about if there's a way to delay those dense updates, right, or somehow avoid those dense updates. So this is another case. So interestingly, you know, at some point, after I read Bob Carpenter's thing about the lazy logistic regression method, I started thinking about this algorithm again. So I'd actually implemented this, and I knew people in industry that had implemented this and said, yeah, it is very slow because you've got to do those updates, you know, those dense updates. So for big data, there are lots of features, it gets expensive. So the average perceptron, maybe there's like a better way of doing it. I don't know. But this was like something that we thought about and then sort of hadn't followed through. And then when I read Bob Carpenter's piece, I said, oh, I bet I could figure out how to do this. So I kind of figured this out. And after I figured it out, I did this big literature search to see if I could find anyone that had mentioned it. So Leon Bateau, who has implemented some really nice online learning methods, he's famous for his work on SVMs, for example, online SVMs, had like a little blog post, or maybe it was like a message in a comment where he basically said, oh, you can do it this way, so it's not really that expensive. But as far as I know, it's not really out there in the literature. But it's a nice trick. Any questions? Okay. So I'm now going to take another kind of long sideways run at something. I'm going to spend a little bit of time talking about kernels. and I'm going to go from kernels to the hash trick that we talked about last week, and that you guys are maybe implementing right now. Perceptrons are actually a nice algorithm because they also give you a very easy way to talk about a number of important extensions to learning algorithms. So I'm going to use that for that purpose for the next few groups of slides. So what I'm going to talk about is kernels. Okay. So there's something called a kernel perceptron. So what does this look like? All right. So what we're going to do here, normally we just compute this dot product, and when we do an update, we just do this, right? So there's another way of doing something which is equivalent, and it's based on this same idea, okay? So VK is actually the sum of a whole bunch of things, right? It's the sum of all the examples you've made mistakes on in the past, right? And each one multiplied by an appropriate label, +1 or -1, right? So we could write that out. We could look at all the cases. So there's basically two cases where I made a false negative, right? So that's where the label was positive and I said negative, right? So all these guys would basically get added into VK, and the other ones where I made a false positive, they'd be subtracted, right? So I could write this as, I could replace VK with, basically the sum of all these guys in Fn minus the sum of all these guys in Fp, right? And then I could just distribute that, all right? So another way of saying this is basically of making this decision is, well, I'm going to compute these two sums, right? So these are the ones where I thought it was negative, but it was really positive, right? So these are examples that have a positive class that are somehow important or were important in my online process. And these are conversely examples that had a negative class. So what I'm going to do is I'm going to look at inner product, which is sort of similarity metric, all right, for all the positive examples and add that up. All right, I'm going to compare that to inner product with all these, negative prototypes and add that up. And, if this one is more than that one, there should be a sign here, right? If this one's more than that one, I'm going to basically use, say positive, otherwise I'll say negative. All right, so this is exactly the same algorithm, right? I've just sort of broken the sums out differently, all right? It looks different, and it maybe gives us a little bit of a different insight into what the algorithm's doing, okay? So this is exactly the same as before, okay? But it's now sort of expressed differently. Now the decision isn't basically, inner product with some hyperplane. Now the decision is, how similar are you to some set of positive prototypes versus some negative prototypes, all right? So the really cool thing about this is we can plug in a different measure of similarity. So here similarity is inner product, okay? But we can generalize that. This is the basic idea behind the kernel trick, all right? So we're going to replace this dot product with another function, which I'm going to call the kernel function, okay? So this thing now becomes the sum of all the x's in this false negative set, the ones where we gave it a false positive prediction, minus these, okay? So all I've done is basically replace the dot product here with this arbitrary kernel function. So this is the form of a classifier that's produced by a kernel machine. So it's basically a weighted sum of the kernel similarity between your test example, which is I guess xi here, okay, and a bunch of examples that you've chosen as prototypes, which are called the support vectors. And for the other kind of widely used kernel algorithms are more general than this, so the weights aren't always just 0 or +1 or -1. So instead it's just sort of a linear combination of similarities over prototypes. Okay. What kind of kernel functions can you use? So inner product you can use. There are a bunch of other things that are commonly used. So one that's nice is inner product +1 raised to some polynomial. So square it or cube it. This is another one where you basically take those two things, you look at a difference, and then run through an exponential. Okay. And I'll talk a little bit more about these later, but there's lots of kernel functions that people use. I'm going to actually skip over some of these because I think this might be a little, well, yeah, let's just say it's maybe a review for people, but it's maybe worth doing. So some fancy terms that people use. One is duality, which is basically a way of talking about the fact that there are two different ways of looking at this same problem, right? So either you're predicting things with the sign of, this kernel function between an example and a weight vector, right, where the weight vector happens to be of this form, right? Or you're treating this as a sum of kernels between your example and these prototypes, okay? In general, the kernel functions I showed you on the last slide can actually all be rewritten in a particular way. They could all be rewritten as the dot product of x after some pre-processing step. So here my preprocessor is this function phi. In the general case then, right, we're looking at a weight vector that's in this transformed space. We've taken our examples and transformed them, and then we multiply by a weight vector in that transformed space. All right, or we can do it, in the dual space. So we can look at the transformation of my test example versus the example on my prototype. Okay. So these are basically two different ways of getting exactly the same behavior. All right. In this left-hand side, we're explicitly mapping from x to some pre-processing step. So if I'm just using inner product, that's just the identity mapper. Okay. This is called the Hilbert space associated with the kernel, right? And here, we're not doing that explicitly. Instead, we're implicitly doing that map by just changing the kernel function. All right, so here we never basically look at the transformed thing. We just look at the kernel, which is defined in terms of an inner product on the transformed thing. Okay. So if you're using a kernel algorithm, the only thing you really need to know is the similarities between all the examples in your training set. Okay. So that's sometimes called a Gram matrix, right? So basically, it just, it's n squared, where you have n examples, and it will tell you the similarity according to the kernel function between those two examples. Once you've got that, the rest of the algorithm is sort of fixed. And there are a few mild conditions. So the condition is called that it's positive semi-definite. This is sort of the technical condition, but there are basically some mild conditions on this. And if those conditions hold, then you can be sure there actually is a transformation of the examples that corresponds to that similarity function, and then that all the math should hold, right? And what you're really doing is you're just doing learning in the space of this transformed function. All right? So this is really interesting to think about in terms of the math we did for the perceptron algorithm. Okay? So the perceptron algorithm should converge whenever we have a large margin for the examples, right, relative to some unknown classifier. And once we introduce the kernel function, then we're basically looking at a large margin in the transformed space. So when you do use things like the polynomial kernel or a Gaussian kernel, then what you're essentially doing is you're mapping things into a much higher dimensional space. But fortunately, the perceptron algorithm doesn't care that the space is higher dimensional, right? The dimension of the examples doesn't come into the mistake bound. The only thing that comes into the mistake bound is basically the size of the example. So if transforming them makes them much larger, then that could slow down the learning, right? And the other thing is the margin. So if things are clearly separated in this new space and they weren't before, you could get a big win. All right. So that said, these sort of explicit kernel algorithms, where you either have to do a lot of similarity computations on the fly, or worse, compute the whole gram matrix, those aren't really scalable to large data sets. It's very expensive to do a lot of similarity computations, so you usually don't want to do that explicitly. All right, but it turns out that kernels are a reasonable way of talking about something we've already talked about in this class, namely the hash trick, right? So if you remember for the hash trick, what did we do? We started with this algorithm where basically we were updating examples. We were updating a weight vector W based on our example, right? And then we said, well, what I'm going to do is I'm going to take that example, which is like this long feature vector, and I'm going to hash each of the values into a smaller dimension, a dimension, let's say, a size R, right? So I'm using an array of size R. I'm hashing things into this. I'm not caring about collisions, so that we have a sum because we're adding things up when they collide, right? So this is a transformation of the data, right? So this is a transformation. And one question to ask is, is it the case that this transformation is a transformation that corresponds to a kernel? Because if that was true, then we could say a lot mathematically about what this trick can do. Right now, we can't say very much mathematically about what that trick can do, right? So, the key thing that's happening here is we're basically using weights in a new space, and we're using a transformation of the data, right? This is an explicit transformation, not an implicit one that's done by changing a similarity function in a kernel algorithm, right? It's an explicit transformation, but the theory behind kernels is all a theory about transformations, right? So any transformation that's sort of where the similarity is equivalent to some inner product in the transform space is fine, right? So, can you make this into a kernel? So you might be stunned by the lead-up I've given to this to find out, yes, you can. So there's another nice paper by John Langford and a bunch of other folks. The theoretical version of this is a little bit different. The hash function I described actually will sort of systematically bias the values in one direction or another. So a way to avoid that is to basically whenever you hash something, you generate two values. You generate the hash index, the index into that array, and you also generate a +1 and -1, and those are just taken uniformly at random. So you're either going to add or subtract. So this has actually a nice property that you don't actually change the expected value of the buckets, all right? Normally when you make the dimension smaller, you'll make the expected value a little bit larger, all right? So they basically do a lot of math, but most of the results aren't very surprising, right? So the claim is that this variation of the hash function, the expectation of the dot product, this little bracket notation is dot product, okay, in the transform space is the same as before you transform, okay? And you can also put a bound on the variance, all right? So the variance is something like 1 over m, where that's the number of buckets you hash into, or r in my discussion, okay? So they basically show that this, in fact, it's not an inner product, but it's an approximation. It's a stochastic approximation to an inner product. You can say things about how likely you are to get something that's different. So each of the individual values has some particular variance, and we can sort of aggregate that. And we can say, how far are we likely to be in general? You can also say something basically about what the likely difference is between the true inner product and the hash space inner product, okay? So the basic story here is that the inner products aren't changed too much by the hash function. And all these things, sort of the dominant term is 1 over m, which is the number of hash buckets, which will normally be big, right? So normally, that will be thousands, right? You'll have many, many, many different buckets. Yeah. Yeah, that's kind of the short story, I guess. This is one formal explanation for why we might see results like this, where what we essentially see, something that converges really pretty quickly to the right, to the answer you get if you didn't use the hash trick, okay? But also kind of opens up the door to using really, really large spaces of features. Okay, are there questions on that?
What's the personalized version here?
Oh, we talked about this last week. This is this email classification task, all right? So in the baseline, you're basically using bag of words features, okay? In the red line, what you're doing is you're using bag of words features that have been personalized. So we have one version of the word for every user, right? And we're doing email filtering and averaging over many different users. So, you know, I forget what the numbers were for the vocabulary. Maybe it's like millions, a few million. But this line was like 16 trillion, right? So this was way bigger than you'd want to put in like a hash table in memory. So this is basically showing you can do things that you couldn't normally do. So that's basically a really big feature space. Yeah.
What's the intuition behind choosing various kind of kernel functions?
What's the intuition between choosing various kinds of kernel functions? So that's really a hard question to answer. So the kernel function ideally would reflect the kind of similarity you expect to see between examples of the same class, right? So you're really sort of designing some function that you believe is going to be sort of a reasonable distance metric for the task and for the data that you're looking at. I don't think there's really sort of a good rule of thumb for what that is. The ones I showed, these classes right here, are sort of the most common ones. So this ends up being something a little bit like a nearest neighbor method, because essentially you're only weighting things that are really quite close to the example. You know, everything else, if it gets the further away it gets, the faster it drops off. Okay. This function here, the polynomial kernel, is kind of qualitatively the same as the linear kernel, but it tends to do better when you have more data. So the degree of the polynomial, you will usually set it to be larger for when you've got more data. So it tends to change the space so you get more separabilities, but of course they're more kind of to look at. So I mean, generally when people are using a kernel method, they'll explore different kernel types. And there's a big literature. I'm not really talking about too much in this course because it's not really a big data thing. But there's a big literature on designing kernel functions for certain tasks. So often looking at structured objects like trees or graphs, how can you construct a kernel that will be a reasonable distance metric for those? That was a good question. Thank you. All right. So I started out by saying the cool thing about the perceptron is you can use it to play a whole bunch of tricks, right? So one trick you can play is the kernel trick, right? The kernel trick is a little bit like the hash trick. Here's another trick you can use with a perceptron. So you can also use perceptrons, and average perceptrons and so on, for ranking, all right? So this is a different API, okay? So again, we've got an adversary and we've got a learner. The adversary sends not a single instance and to classify, and says here's a whole bunch of instances. I want you to rank them, okay? So B doesn't have to send back a whole ranking. It'll just compute the one it thinks is best, okay? So how does it figure out which one is best? It just does a dot product. So it's got some hypothesis weight function. It looks at the dot product of every example and comes up with the one that has the highest dot product, okay? So that's the best thing. It sends it back, and then the adversary says, no, this is the one that really was the correct one, okay? So it sends back the index of one of these things that it thinks is best, and the adversary sends back the correct index. So if you want to like imagine, an example of this, let's say we're like learning to rate movies or something like that. I basically send you like sort of like a proposed like Netflix queue, right? And what the learner's trying to do is put the things you really want on the top, okay? And then at the end of the day, you find out which one is actually really best, and then that's kind of what you try and train the system to do. Okay, so this is the game, all right? So we're still doing something with an inner product, all right? We're just, instead of looking at the sign, we're basically saying which one of these candidates is best, all right? And we can get very similar mistake bounds if we make a similar or analogous set of assumptions, okay? So here's the assumption. So my assumption is there's some weight vector u, okay? So whenever I give you this example, right? So this is a set of things to rank, and then L is the true best, the index of the true best one, all right? Then I want to basically say the best one is best according to you, all right? And furthermore, there's a margin property. The best one is better than the next best one by at least gamma, right? So the way to say that is basically the inner product with x sub L, the best guy, the true answer, is more than the inner product with xj for every j by at least gamma, all right? And then I have the same size constraint, okay? So this is the margin. The margin basically says, yeah, the best thing is always kind of clearly better than the rest, all right? And then the other thing is basically the same. It's giving examples near the origin. So it's a constraint on the size of the examples, okay? And then the update is actually, I didn't give you the update, but the update is basically also kind of similar, right? So I'm going to take the old example, and I'm going to update it, all right? So the best one was XB. I'm going to add that, all right? The one I thought was best is XB star, and I'm going to subtract that one, all right? So before I was adding something if it was positive and subtracting if it was negative. Now you can think of this as there's one that's positive. That's the one you gave me back here, right? And there's one that's positive and there's one that's negative, right? So I'm going to add the positive one and subtract the negative one. So it's very analogous. All right. So here's the picture. All right, I'm using the same u vector. I get a bunch of examples, right? So these x's are the things I have to rank. All right. So if I knew what u was, then I would rank them by the dot product. The dot product is basically just the projection along u, right? Okay, so I just project these things along u. And the margin requirement here basically says that the one that's really best should be at least gamma away from the second best. Okay. All right. So that's kind of what the picture looks like. And here's sort of an example of what the learning would look like. So here, let's say I've got some other hypothesis. This V right here, okay, this purple thing. All right. So this is what I think the hypothesis is. So I look at the dot product with this V rather than U. Of course, I don't know what U is. That's the kind of oracle, right? So the dot product with those means basically projecting along those, okay? And I'll pick the one that has the highest value. So it's the most positive projection. That's this guy right here, the one I circled, all right? But the one that was actually right is this one, okay? That was the one that sort of had the best projection along this blue line, okay? So this is what I think is best, and this is what's actually best. So the update then, I basically want to subtract this and add this, right? Okay, and I subtract this and add that from V, okay? So adding this and then subtracting that should get me to somewhere like that, okay? So that's the update you'd make, all right? Which in this case gets you pretty close to the right answer, okay? So let's just kind of go through that again. So here's the picture. These x's are stuff I want to rank. And the margin constraint says that the one that's best is actually kind of clearly separated from the next best one. So these could all be in, this part of the circle or that part of the circle. It doesn't really matter. There's no positive or negative here. There's no right or wrong. There's just best and, not the best. Okay? It's kind of like, instead of like taking a class, you're playing Survivor. Okay. So this is your guess, and we're going to see how this gets changed, right? So we're going to look at the inner product with that guy, so we're projecting everything onto that. This is the one that has the highest score, right? So that's what the learner would say is correct, right? This is the one that's actually correct, so the feedback it gets is, no, this is the guy that's right, all right? So this becomes your negative example, that becomes your positive example, you update your weight vector, and then there you are. Okay. All right. So that's kind of the story. Let's see here. So now let's do the math, okay? So we did this math Thursday. But this is, of course, totally different math because it's a different problem, different API. It shouldn't look anything similar, but you might find this somewhat familiar. So the first claim I'm going to make is a dot product between VK and U increases with each mistake. So we're getting converging to the right answer in terms of dot product, okay? What we do is, once again, what we did last time was we basically looked at the definition of VK and then we sort of simplified it and plugged it in. All right. So here I'm going to do the same thing, sort of. Okay. I'm going to look at the dot product between VK and U. I'm going to see how it increases. And to do that, I'm just going to basically take that and plug in the definition of VK plus 1, right? So this is XIL minus XI, is that L hat? I guess it's an L hat, right? Okay. And then we just distribute over that, okay? And once again, I can see there's VK.U here, right? And then I know that this quantity minus that quantity is more than gamma, so I'm done, okay? So it's basically the same sort of analysis, not really much different. We just kind of plug in the definition of VK and then it sort of like naturally emerges. All right. And once again, this is something you can sort of see. So here you could sort of see it because whenever you add an example, it's at least sort of gamma in the right direction. Here again, we get the same kind of story. I've got a positive example and a negative example, and they have to be separated by gamma in the direction U. So when I subtract the negative example and add the positive example, since their separation along this projection line is at least gamma, then I've increased my dot product with U by at least gamma. So it's still the same kind of visual argument, if you like. So the other argument is this doesn't grow too large, okay? So what I had before was I had a constraint that basically said the square of the hypothesis with itself, the dot product of the hypothesis with itself, is no more than 2k r, okay? Before it was just 2k, all right? And the analysis was basically, well, I'm always adding one new example. Size of the example is bounded by r, so that should hold. And that analysis basically just kind of goes through sort of without really any change. I don't have it here, but it's basically the same analysis. Okay. All right. So this gives us the same proof, okay, or a very similar proof, right? Once again, under the rules of this game, okay, we're going to get a bounded number of mistakes. And you can do the same thing with delta tricks and so on and so forth. All right. So that's another cool trick. So you can use the same algorithm or almost the same algorithm for ranking, which is another big problem. So re-ranking is used a lot in IR, click-throughs and so on and so forth. So it's an important problem. So now I'm going to talk about yet another trick you can do with perceptrons. All right. So this trick is called structured output perceptrons, or just structured perceptrons for short. All right. So this is another API change. All right. So the first API change was basically I went from positive, negative examples to a set of things, and you pick the top one out of that set. So choosing the best from a group. All right. So now we're going to take this ranking idea and we're going to use it to do structured prediction. So for ranking, this is what the API is. We get a set of things. So notice in the analysis about the mistake bound, I use the margin, I use the size of the examples. I didn't use anything about the number of examples, right? So the number of the examples didn't come into that mistake bound at all, right? All that really mattered is the size of the examples when you're adding them in, and then you're only adding in, two, one positive and one negative each time. And the other thing that mattered was the margin between the best and the next best. Okay, so you could possibly send a really huge set of things to be ranked. Okay, that's fine in this ranking game. All right, and then the learner finds the best one and sends it back, and then it gets feedback as which one is actually best. All right. So structured classification is different. So a typical example of structured classification might be something like part-of-speech tagging. So you have a bunch of words, but they're not independent examples. They're all words that are in the same sentence. So these are words that are in a list, okay? They're in an ordered sequential list. And then what you get back is one label for each word, okay? So if you have like 40 part-of-speech tags and you've got 10 words, right? You've got 40 to the 10th power possible labels for that sequence, right? And we're not going to treat everything in that sequence as independent. We're not just going to treat it as like a bunch of separate classification problems and separate classification problems. What I'll do is treat it as one big classification problem so I can think about the dependencies between nearby labels, right? Okay. I can't hear you. I've got a banana in my ear. Okay. Let's see. Okay. So this is like ordinary classification, but there's a huge number of possible labels. All right. So here are some examples. So one task you might look at is segmenting records. So here I've got just like a big long citation, maybe out of a paper, and I want to break this up and sort of figure out, what are the different parts. So this yellow stuff is the author, right? That's the year. This is the journal name. This is the title. Pages, volume, things like that. Okay. So you could, and these labels are correlated, right? So the author name is kind of this long block. So if you see one author label for one word, like great car, then the one word next to it is probably like going to be an author too, right? And same thing for most of these, right? So there will be some order dependencies between these. Another example, which is actually kind of quite similar, is recognizing names in a string. So maybe you've got a string like this. When will Professor Cohen post the notes? And you want to basically do a classification of the tokens and tell whether they're part of a name. So a common thing to use is to basically use a set of 3 labels. So O means they're outside any name. B means they start a name. And I means they're inside a name, but they're not the first word. So you can do that because if you might want to say something like, tell Buwan William's on the way, right? So Buwan, William are 2 different names. So you put a B here and a B there, then you could tell they're different. So this is called the BIO labeling for named entity recognition. What you'd like to do is you'd like to be able to write features down. So it turns out you can write features of any individual thing, like, is this word capitalized, or what's the word to the left of it, or what's the word 2 spaces to the right, and maybe those are good features, maybe they're not. Another thing you can do, and which is commonly done in named entity recognition problems, is to construct features of 2 adjacent tokens, right? So you might say, well, this is a B or an I and it's capitalized, or you might say the one to the left is an I and the one to the right, and the one, the token here is an I and the one to the right is a B, okay, and that token at this point is hyphenated, right? Or you might sort of say, well, I've got 2 B labels in a row. How likely is that? So for some reason, this whole thing just went dark. Doesn't seem good. Well, nobody can see it but me, so anyway. So this turns into a situation, supposing I have a weighted sum of those features. So each of the features basically corresponds to an edge. And really, it's sort of an edge between 2 possible labelings of a particular word. So you can think about this sort of graph. So I've got all the words in the sentence. I've got all the possible labels you could apply to each word. I've done some sort of weighted combination of the features. So I basically have looked at a dot product between a weight vector and the features associated with a particular edge in this graph. So each one of those features depends on the labels I'm thinking about assigning and anything else I want from the sentence. Once you've computed those weights, what you basically have is basically a path-finding problem, right? So if the weights are heavy, then that basically means there's low cost of including that edge. And if the weights are low, then there's a high cost. And what you basically want to do is you want to go through and find the highest weight path that takes you from the left-hand column to the right-hand column. Okay? So that's a little problem, optimization problem you have to solve. So once you've got a weight vector, you can find you want to find the highest weight path. You can do it with a dynamic programming sort of path-finding algorithm. It will be a nice little assignment to figure it out. It's not complicated. Very related to HMM computations. Okay? So this actually is the key towards turning this ranking problem into a structured output problem. Okay? So here we know how to rank things. All right? Here my goal is, given a list of things, choose among the many, many different possible labels for those things. Okay? Right? So I've got k to the n possible labels for the sequence. All right? So here's my new API. So I'm going to take this problem and reduce it to ranking. Okay? And all I'm really going to assume is that I can do this kind of path-finding problem. I can find the heaviest path relative to some particular weight vector. All right? So here's the algorithm. Okay? So I send B the actual word sequence. Okay? B has a weight vector. Okay? And it knows how to run this Viterbi algorithm. Okay? It knows how to find the best path. All right? So it does that, and it finds the best labeling. So this is the best labeling Y for that sequence of words X. Now there's 2 to the n possible Ys, or k to the n possible Ys. So there are lots and lots of different choices, but that doesn't matter. Okay? The Viterbi algorithm is very efficient. Right? It's just linear in the size of that graph. It's not exponential. So the time doesn't really hurt us too much. But the other thing that's nice is that the fact that we're sort of implicitly looking through k to the n possible answers also doesn't hurt us too much. So really, we're ranking every possible y star. Let me put this in here. Okay, we're ranking every possible x y pair for this particular x. All right, and returning the best one of those pairs. Okay, but it's not going to. The fact that space is large doesn't hurt us either sort of from a computational point of view or from a mistake-bound point of view. And then the feedback I get is which one is best. Okay? So then the trick is, can we figure out how to update things? All right, so the key step here is that this is going to be exactly equivalent to ranking pairs where X is the input and Y is a proposed output. So what I have to be able to do is basically compute the feature vector for those, right, for a given Y, all right, because that's what I'm getting back. I'm getting at the Y that was actually best, as well as the Y that I sort of had in mind. And I have to find the best Y for any X. So those are the 2 operations I need to do to make this work. So this is the basic idea then. So to go from this ranking idea to named entity recognition. So what B gets is basically the functions for computing the features, all right, and a word vector X, right? Then, in principle, what you could do is you could look at every possible, all the k to the n possible labels for X, compute the feature vector for each of those, but you're not going to do that, right? Instead, you just return the Y star that gives the best score, okay? And we've got some feature vector that encodes that pair, okay? The feature vector is just basically computed, if you want to go through here, It's basically be computed by taking the features for each edge that actually was used in your shortest path. Then A sends you the correct label. All right. So the correct one, the one who's actually best, and the way it does that is basically just sending you the correct label sequence. All right, and then you do an update. All right. So you'll take your old weight vector and you'll add in GB and subtract GB star your guess. And here, this is basically the feature vector associated with the correct label sequence. And what you subtract off is the feature vector associated with the incorrect label sequence, the one that you return to A. So this is an old idea. This kind of goes back to like 2002, an EMLP paper by Mike Collins. He had a bunch of cool results on this. One thing that was one reason why this had a lot of impact is because this is really a very common problem. We've got some tasks we want to solve. Okay, in this case, it's labeling a sequence. We can find the best thing in the best label for a particular hypothesis, but I want to tune my hypotheses. So how do you tune the hypothesis when all you can do is sort of give you get the best prediction, the Argmax score for the labels at any time? So this is something which happens all the time, particularly in language-like tasks. So it's a very widely used technique in language tasks. So here are some of his examples, his baselines. So here it's called ME, but what this really was logistic regression. And this was before we did regularization. So this is using logistic regression, and you're doing a cutoff of the number of features. This is using features that occur at least 5 times in training. Okay, this is all the features in training. These are the perceptron algorithms. So basically, the short story is with averaging and without any feature pruning, they do as well or better than the Maxent logistic regression methods. And the logistic regression, I should say, it's also doing this kind of Viterbi trick. So you're sort of trying to find the best sequence using the similar sort of features. Okay, so there are questions about that? All right, we're not going to get too deep into this now, okay, because we have like, I guess, 15 minutes left. I want to spend a little bit more time on this. But the next thing I want to talk about is this paper here. This is from NACL 2010, right? And this is one of the kind of clearest and nicest papers on distributed learning. So it's all based on perceptrons. And in fact, it's based on what we just sort of led up to, the structured perceptron, which is based on this ranking perceptron. All right. And they were using these perceptrons for a couple of different tasks. One was tagging the named entities in a sentence. The other one was constructing a parse of that sentence. So again, you have a parser, you've got a bunch of features which you can compute locally on the parse tree, and you can do some clever dynamic programming stuff so that you can find the best parse for a particular feature weighting scheme. And that's the kind of essence of what you're using the perceptron for, basically learning how to do better and better parses. Okay, so what they did was they looked at ways of taking that algorithm and running it in parallel for large data sets. Okay, so the simplest thing you can imagine doing is basically just taking the data, splitting up on a bunch of different processors, okay, learning a perceptron on each processor, okay, and then combining those perceptrons at the end with some simple way. So one possibility would be just to do a weighted average of those perceptrons, maybe just an average of the perceptrons, or maybe it's weighted by the size of the training set, because the training sets might not be exactly the same. So, so this, of course, would be a lot faster, right? because we're running the perceptron separately on 10 times or 100 times on 1/10 or maybe 1/100th of the data. Okay, so this would be a lot faster. So the kind of pipeline would look something like this. We take our instances and labels, we just shard them into 3 different pieces. Then we run through this, we come up with some hypotheses, okay? Maybe these would be the average perceptron at the end of each run, and then we average those out one more time, okay? So that's one possibility, okay? Sometimes this kind of distributed learning does work, okay? So sometimes you can start off, run several processes separately, then combine the results and get a not terrible result. You can certainly construct examples where it doesn't work well, okay? So you can construct an example where, for example, even though every shard gets, you train every shard so you get 0 error rate, and then you combine it, and the average vector would still have a high error rate on the training data. So you can certainly come up with cases where this doesn't work well. So then they explored another strategy. So this is the second simplest strategy you might imagine, all right? So the first strategy was basically we split the data, we run the learners separately on the data till convergence, and we combine the results. All right, the second strategy is, well, let's not run them till convergence. Let's just say run one pass through the data, okay? So we'll just basically do a little bit of learning for each of those shards. Then we'll take the results and then we'll combine them. Then I'm going to take that combined result and I'm going to redistribute it to the different worker machines. And then each worker machine will run perceptron again, starting with a different weight vector, starting now with the one that was the average of the results from the first round. Okay, but using the same data, I'm not going to redistribute the data, so it's going to run through the same data again. We'll basically sort of keep doing that. All right, so we've got this loop now, right? So in the inner loop, we're going to run this perceptron for one epoch, starting with W. All right, W starts off just being, the kind of empty vector, 0 vector that we start off perceptron with. And then, but after each epoch, we're going to average out the results from the previous epoch, and that's my new starting point. All right, so I do this multiple times, okay? So this is a name, it's called iterative parameter mixing. The picture is basically this, okay? So now each thing gets 2 inputs. One is the last hyperplane, the last hypothesis, all right? And once you average things out, you kind of go back around this loop, all right? So that's the algorithm we're going to spend a little bit of time analyzing on Thursday. And I'm not going to jump into the analysis now, but we do have a special offer, okay? Just for today, we have a special offer from Julian. So, I have to tell you, like a year or two ago, somebody made me like one of these offers. It's like, I know you've got a big class, and I want to get some people to do a study involving machine learning algorithms. And anyone that participates in this will get a free lunch. Okay? So I'm not sure if Julian can make that offer or not. But we don't know. This is another similar sort of deal. Come on up.
It's almost lunch. Probably more than lunch.
It's past lunch. It's past my lunch. All right.
Hello everyone, my name is Julian Ramos. I'm a second-year PhD student at Human-Computer Interaction Institute. I want to invite you all today to participate in my research study in which you get to do to work on a data science problem. You are just going to the data set and you figure out. I cannot really tell you more details. Just go to the study. I'll hand out the link for the study. You can do it anytime, it's online, and you get paid $20.
Ooh, $20. That's more than lunch.
Yep.
Okay. All right, so that's the special offer. So you can do that, and it's for so
Yeah.
even better. Okay, so I will see you on Thursday.
Thanks so much.
Okay, maybe you'll be $20 richer.